Okay, this is Mr. Smith, and we're doing this video on, what is angular displacement, what are radians, and how do we convert radians into a distance in meters or an arc length. And so to do that, I've got this little ladybug going around on a turntable. I've drawn in some radian angles that we'll talk about here in a second. And we're just letting the ladybug go around. First off, when we're talking about angular displacement or all of our angular quantities in this class, if it's spinning around counterclockwise like this little ladybug is, we'll say that's a positive angular displacement. And angular displacement is just how much of an angle has something spun through or revolved through. So if you watch that ladybug go around, from where it started down at 0 to up there, we'd say its angular displacement was 90 degrees. Okay, or as it goes all the way around the circle, we say the angular displacement is 360 degrees. It's going to be much more convenient, though, for us to use a degree of radians. And I've marked out some radians already here. So, for example, between these blue lines right here, that is 1 radian. And we can just put RAD for a radian. And so we're going to be measuring our angular displacement, how far something rotates or revolves in radians. And that is defined by something that's rotating traveling the same distance as the radius. So for example, this little ladybug, if I follow the ladybug along, I'd stop right there. That distance that I marked out is 1 radius. The radius of this happens to be 4 centimeters. So this arc length distance that I drew would be 4 centimeters, and it would be equal to the radius. And so that marks out this specific angle. And so that angle is 1 radian. And so let me erase this so I don't confuse a point. The advantage of doing that is when we want to convert our rotational units, like a displacement, like an angular displacement, into a distance or linear units like meters. How far did that bug actually travel in meters? Maybe we want a speed or an acceleration or whatever. We can do that with this very simple equation where the arc length, we use S to measure a distance or an arc length, equals the change in the angle, this is our symbol for angular displacement, times the radius. And so let me give you an example. Let's let this ladybug come around, and then I'm going to let the ladybug go through maybe like 2.5 radians of angular displacement. So I'm going to start it when the ladybug gets at 0 right there, and we'll let that ladybug go and try and hit. Oops, let it go a little more. Let's go. That's pretty good. Let's say that's 2.5 radians. All right, so the ladybug started here. So I'm going to say this ladybug started right here, okay, and went all the way around to this point. Well, here was 1 radian, and that distance is 4 centimeters. That's how it's defined. From here over to here, that was 1 more radian. So here's another radian. And that again was another 4 centimeters because that's defined by the ladybug traveling the distance of 1 radius. And so here, this angle is about a half a radian. And that would be half the distance around or 1 radius. So that would be 2 centimeters. And so we have this ladybug traveling this distance of 10 centimeters, but we can calculate that. Often it's not going to be that easy to just know exactly 2.5 centimeters, or maybe the radius is some weird fraction that makes it hard to do the math in your head. We just take our angular displacement, which was 2.5 radians. We multiply it by the radius. In this case, the radius is 4 centimeters. I can show you that with this ruler. So the radius here is 4 centimeters. That's why this distance is 4 centimeters. Okay, and so let me fix this. So yeah, 2 pi radians multiplied by 4 centimeters as the radius, and that turns out to be 10 centimeters as the arc length that it traveled. One important kind of note to make, and let me close this up here, is that if we have another object on this same disk, you'll notice the radiuses are much different. If I pull this back up, if I allow this ladybug and this beetle now to travel together, their angular displacement is going to be exactly the same. But this length that the beetle travels is much, much less because its radius is much less. You can think of the distance the ladybug travels all the way around the circle is 2 pi times its radius, and the little beetle's distance all the way around the circle is 2 pi times its radius. And so even though their angular displacement is going to be the same, they're going to make the exact same angle, their distance they travel in meters, sometimes we'll call that a linear distance. In this case, since they're objects traveling around a turntable, we'd call it a translational distance. That is going to be very different. And so when you have a rigid body like this and you have something turning around, on that rigid body, anywhere on that is going to have the exact same angular distance because it's going to make the same revolutions in the same amount of time. But their actual distance in meters is going to be much different.